The objective of this video is to update the analytic machine design procedure for cage rotor induction machines and outline FEA-based design evaluation steps for optimization. This video is intended to be based off of or compared against a previous video that we had on the analytic machine design steps. So this video revises those lecture notes for this cage rotor induction motor. So what I'm going to do is I'm going to go step by step through the steps that we outlined in this previous video. The step numbers will correspond. So step 1 in the previous video was on the design specification. Step 2 was on the main dimensions of the machine. So we're going to go step by step and talk about how those steps are either the same for the cage rotor induction motor or they are different. And we'll try to give as much perspective as possible when it comes to designing these motors, but I want you to realize that every design is unique. So this is the same disclaimer that I made in the design sizing video for a general machine, which is that as a designer, it's your job to use your engineering wisdom to figure out whether you should follow the steps that I'm presenting here or whether different steps are warranted. So these steps are intended for kind of a general vanilla case, and any given design for a application may impose unique specifications or constraints that require a rethinking of these steps. So these steps should be the baseline against what you compare your efforts to, but if these steps are oriented towards the most mainstream case, so perhaps a 2-pole 3600 RPM motor, and say that you're designing a 4-pole 60,000 RPM motor, well, clearly these steps are going to need to be modified, and the models and the assumptions that are made when creating these steps are going to need to be modified to create that type of design. So keep that in mind. You have to use your engineering wisdom to modify what we're showing here to make it apply to your specific use case. All right, so the first step in our original video was on obtaining a design specification that's used to drive all the remaining steps. And the same considerations are present here when you're designing a cage rotor induction motor, but I do want to comment on a few nuances and differences that come about when designing this kind of machine. The first is that the induction motor is inherently a lower cost machine. It does not have any permanent magnets on its rotor. It doesn't require any brushes or slip rings like a wound field synchronous machine does. So this machine is only made up of laminated steel and either copper or aluminum. So an important design specification when it comes to design one of these is to think about whether you want to use a cast aluminum rotor or a copper rotor. Copper rotors are more expensive, but they're going to be a bit higher efficiency because the conductivity of copper is better. Cast aluminum rotors are low cost. You can make these at scale at very low cost because you can set up a standard manufacturing line that's casting aluminum into cutouts in your laminations. So it can be very low cost and quick to produce, but you pay that efficiency penalty because the conductivity of aluminum is lower. The second thing is that in an induction motor, you're going to have a lower efficiency. This is primarily due to the addition of rotor current on your rotor and the requirement that your stator carries magnetizing current to magnetize the machine. It is also due to the fact that your rotor is exposed to alternating fields because the rotor speed is not synchronous. So the rotor sees an alternating field, and that will cause some small amount of iron losses on the rotor. And also, induction motors will have a lower power factor. We talked about how power factor relates to the amount of magnetizing current versus torque producing current that you have in a previous video. In addition to that, we can comment that as you increase the number of poles of your machine, your inductance, your magnetizing inductance of the machine goes down by P squared. So you end up needing more magnetizing current as you design towards higher and higher pole combinations of induction machines. And for this reason, typically we see induction machines as being either 2 or 4 pole machines. Sometimes you'll see a 6 or an 8 pole induction motor, but those are pretty rare. And you really never see induction motors that are over 8 poles. The third thing that is unique to induction motor design is you should consider whether or not this machine is going to be designed for line-fed operation or whether it will use a variable speed motor drive. This distinction poses different requirements for what your torque slip curve should look like. If you're operating off of the line, you need to be very careful that your torque slip curve avoids significant local minima and maxima, like we talked about, so that you avoid your rotor getting stuck at a speed you don't want it stuck at, so that you can always reach your breakdown torque. If it's a variable speed motor drive, you have some more leeway here because you can kind of customize this torque speed characteristic using your variable speed motor drive. And the final thing that I want you to think about when you're thinking about the design specification for an induction motor is whether this is going to be operated at a so-called standard speed or whether it's going to be a high-speed machine. And by high speed, I'm talking about speeds significantly over line frequency, so significantly over 3,600 RPM. When you get to really high speeds, induction motors are sometimes favored because you can do interesting things with a rotor, like have a solid rotor that has good structural integrity, and maybe doesn't even use a cage winding. But at that point, you need to start thinking about how you might put geometric features into your rotor to help improve efficiency. So you might add some kind of etching pattern to cause current to flow more axially. So these are all things that should be thought about at the design specification phase that are not necessarily present in the synchronous machines that we talked about earlier. The second step is determining the main dimensions of the machine. And just like in our previous video, we're going to use the machine sizing law. And just like in the case of our previous video, this equation can be expressed as the volume of our rotor times a shear stress. But what's unique about this case is that I recommend you don't break shear stress down into magnetic loading and electric loading, and instead just pick a reasonable value of shear stress from table 6.4. And the reason for that, as we talked about in our previous videos, is that magnetic loading and electric loading are not independent in an induction motor. They depend upon each other. So it's better just to recognize that and pick a reasonable shear stress value. Next, you need to figure out how to think about the volume of your rotor. And in our previous video, we talked about this in terms of a maximum surface speed or tip speed of our rotor when it's at rated speed. And that makes a lot of sense for high-speed motors or high-performance motors like a permanent magnet rotor with a carbon fiber retaining sleeve. However, oftentimes for induction motors, we're operating far below the maximum structural integrity of our rotor, and we have other reasons for picking up a diameter or length of our rotor based more upon cooling requirements or a preferred aspect ratio. And so for these types of motors, for line-fed motors, the general recommended practice is that you maintain a certain aspect ratio between the rotor length and the rotor diameter. And table 6.5 of your textbook presents guidelines on this for different machine configurations and types. For the induction motor, it's recommended that this aspect ratio roughly follow this equation here. And this equation is evaluated as pi over your 2 times your number of pole pairs times the cubic root of your number of pole pairs. So this p is not power, it's number of pole pairs. And where does this come from? Well, the same place that a lot of these tables come from. Engineering best practices, empirical data. It's because over the years, engineers have designed so many induction machines. Induction machines are the single most common type of electric motor, and there have been so many of these designed that by observing the general trends and good designs that work well, designs that can be cooled, we can make these kind of empirical observations. It's not necessarily based on any theoretical model. It's just based off of what works when you build it. What is a large data set? What trends are in your large data set of all the designs ever made? And that's where we come up with these tables 6.4, 6.5, this equation, table 6.2. It's not that we can immediately point to a theory and say that, hey, this trend has to be followed. It's instead observed over a large set of all the designs that have been made. And so this is, what we're giving you here is, again, like a type of handbook that you might be handed when you're working at a company for, hey, this is all the motors that this company has designed, and we find that we get the best performance when we have designs follow these trends. So we're giving you inside machine designer knowledge here. And there's no reason that you can't deviate from these things. So you don't always have to have this aspect ratio. It's just a waypoint to guide your thinking. And finally, the outcome of this design step is that you've got a magnetic loading that you just select from table 6.2. You've got the radius of your rotor and the length of the rotor. So in other words, you know the volume of your rotor and its aspect ratio. Step 3 is selecting the air gap length. And basically, we're following the same practices as we talked about in our previous video, but we can be a little bit more specific because we're talking about induction motors. And the general rule of thumb, or the general guideline or best practice, or engineer's wisdom, whatever you want to call it, is to follow this expression for the starting point of your air gap length. And so this expression applies to machines that are designed for 50 or 60 hertz operation. And it's based on the power rating of the machine. So here on the right, we're sectioning it out based on the number of pole pairs. So machines that are 2-pole machines, the air gap length should be approximately 0.2 plus 0.01 times the power rating to the 0.4 power in units of millimeters. Or if this is a greater than 2-pole machine, it should follow this expression down here. Again, this is an observed rule of thumb. And if you're operating at high speeds, 30,000 RPM or 60,000 RPM, typically your air gap length becomes much larger. The key thing in induction motors is that your air gap length is very closely related to your magnetizing inductance. So you want to have a small air gap length to try to maximize your magnetizing inductance. A high magnetizing inductance is good because that means that you require less magnetizing current to support the magnetic field in the air gap. It means your power factor is closer to unity. A low magnetizing inductance will have a poor power factor, and so that causes your drive electronics to have to be designed for a higher volt ampere rating, so it increases the cost of your motor drive if this is operated by a variable speed motor drive. It also increases the losses in the machine because you have more magnetizing current flowing, so it reduces your efficiency. So you'd like to have as large of a magnetizing current as possible, but physically you can't make an air gap smaller than about 0.2 millimeters. It's just too hard. Your bearings just can't keep your shaft sufficiently centered. And so I encourage you to take a look in your textbook. There's different suggested guidelines for higher speed machines or machines with some other specific considerations. Next, we're going to talk about steps 4 and 5 together. So in our previous video, we separated these out, but for reasons that will become apparent in a little bit, in the induction motor video, we're going to combine these into a single step. So we're going to talk about our winding design at the same time as we're talking about how to meet the voltage requirements of our design specification. And when performing your stator winding design, you'll follow the same general steps as we talked about our stator winding design unit. But for the induction motor, it is especially critical that you minimize the harmonics in your winding. And absolutely under no circumstances allow there to be subharmonics. Subharmonics travel at a very rapid speed, and so this will cause immense losses in your rotor and generally pose heating problems and efficiency challenges. So for this reason, you'll never see an induction motor have a fractional slot concentrated winding. It just won't happen. You'll have too much subharmonics, and you won't end up with a good machine design. The reason that this is so critical is that in the induction motor, your air gap length is typically small, and with short air gap lengths means that your rotor is exposed to more space harmonics from your stator winding, so that will cause losses on the surface of the rotor. In addition to that, the surface of your induction motor has this cage rotor on it. So the cage rotor is meant to have currents induced in it, and you don't want those currents to be at harmonics other than your dominant air gap field, both because of losses that are created in it and because of the problematic synchronous and asynchronous torques that we talked about before. Next, the combination of number of pole pairs, number of stator slots, and the number of rotor slots must be carefully considered. So certain combinations of these values are known to produce problematic torques. So this is the asynchronous and synchronous torques that we talked about previously. And certain combinations are known to cause problematic mechanical vibrations that can make your motor very loud. It can also cause you to have structural integrity issues in the motor. So see tables 7.3 through 7.5 in the textbook and section 7.2.6 for a discussion on how to pick combinations of P, QS, and QR. And what you'll find is that for a two-pole machine, there actually aren't any combinations of stator and rotor slots that are deemed to be acceptable. And so then what you have to do is consider introducing skew into either your rotor or your stator. And table 7.5 provides an updated set of combinations here of poles, slots on the stator and slots on the rotor for when skew is used. And by introducing skew, you can find out that you're able to use more values of stator slots and rotor slot combinations. Next, determine the number of series turns within a stator coil in order to meet the voltage specification that was determined in step 1. So this means that you have a certain desired line voltage rating. Maybe this is a 480 volt line-to-line machine, or maybe it's a 208 volt machine. So whatever that value is, you load that over here, and you want your back EMF to be approximately equal to that, but slightly less if this is for motor operation, or slightly more if this is for generator operation. And we derived in a previous video how our back EMF relates to our number of turns, a number of series turns per coil, and the magnetic loading of our machine, and of course the winding factor. So at this point we know all the quantities in this expression except for ZQ. So we determine EM from these two rules of thumb down here, and then we use this expression here to solve for ZQ. This is different than the approach we used to find ZQ in our general analytic machine design steps. In that video, we solved ZQ based on the desired electric loading, based on the desired value of our linear current density. But here, we're instead doing it based on the terminal voltage of our machine. And in the next step, we're going to determine what our terminal current rating of the machine should be based on the efficiency and desired power of our machine. And as I mentioned, we're now going to figure out what our rated terminal current should be based on the power requirement of the motor. So this expression I've written up here, it gives the electromagnetic output power, the amount of power delivered to the shaft of the motor, based off of the efficiency of the motor, the number of phases, the product of our line to neutral voltage and our line current, our phase current, and the power factor of the machine. So you solve this equation for IS hat, and you know all quantities in here already. So efficiency should have been specified in your design specification. This might have been chosen based off of an IEEE standard or a customer's unique requirement. M is the number of phases of the machine. This is typically 3. The US phase is the line to neutral voltage rating of the machine. We determined that that was in our design specification. IS is what we're solving for, and cosine of phi is the power factor of the machine. And if you look at figure 7.24 of your textbook provides you guidelines for achievable and recommended power factor for induction motors of different power ratings and different number of pole pairs in this figure. And so you can see that based on these considerations, number of pole pairs and power rating, the recommended or the achievable power factor varies. And this is, again, part of that engineering wisdom that we were talking about. This is not like a hard theoretical derivation, but rather an observation of what typically happens when you have a good design. So you solve this equation to determine the current rating of the machine. And then you can go and figure out what your rotor bar current must be rated at. And we previously derived that the rotor bar current can be related to our rated stator current and our power factor based off of this turns ratio that we derived in our equivalent circuit lecture. And so now you have a handle on how much current you expect to flow in your rotor, and that will be useful later when we're trying to dimension the slot shape of our rotor and think about rotor losses. Next, determine the allowable current density, or the specified current density for your rotor and stator. And table 6.3 of the textbook provides guidance on this based off of the machine type, the cooling strategy, the power rating, this type of thing. And then for the stator, determine the AWG wire size and the number of strands in hand. And so this exactly follows our previous video on determining these quantities. Steps 6 through 8 of our previous video pertain to designing the stator slot shape, the stator tooth shape, the yoke thickness. All of these steps are identical for the induction motor. There's nothing different about that. Step 9 in our previous video was on determining the magnetizing winding or magnet sizes, and here we're just going to call it the rotor design. So this step is different, and I want to note that first off, we're going to use the same general arguments to design the rotor slot and tooth shape or dimensions as we did with the stator. And so I'm not going to get into the nuances of the area calculations and the thickness calculations because it's exactly analogous to how we figured it out for the stator. However, I am going to talk about options for our slot shape and why we might pick one shape over another shape for the rotor. Figures 6.8 and 7.14 of your textbook present several different and common options for rotor slot shapes. I've sketched some of the salient topologies here in this figure. And so moving left to right, on the left side we've got what's typically called a single cage. This is kind of the generic type of rotor slot shape for an induction motor, for a cage rotor induction motor. Over here we've got what's called a double cage, so you can see that there's a set of bars that are out here on the air gap surface, and then another set of bars that are totally buried inside the rotor. Moving over here we've got what's, so this was called a double cage. Here's a double cage version for a cast aluminum rotor, and then on the far right we've got what's called a round bar rotor, and so this is a little bit more typical for high-speed machines. So why would you pick one of these shapes over another shape? The first thing that comes to mind is, what is the rotational speed of your motor? What kind of structural integrity issues do you expect to have? And at really high speeds, you'd use a solid rotor, and I guess I didn't draw that on here, but you could imagine over here I've drawn just a cylinder. So a solid rotor would just be a conductive steel cylinder, perhaps with a copper finish on it, and maybe an etching pattern to help contour the shape of the current. That is used because it can present very high structural integrity, and you can achieve high surface speeds. It's not used very frequently anyway at low speeds or more conventional rotor speeds. For a conventional induction motor, your bread and butter induction motor is probably going to be one of these three shapes here. So rotational speed is one consideration. A second consideration is whether you're planning to use a cast aluminum rotor or have copper bars inserted into the rotor slots that are then soldered together at the ends. So if you're going to use a cast aluminum rotor, you're going to be injecting molten aluminum into your rotor, and you'd prefer to have your slot fully contained within the lamination. You wouldn't want to have the slot open to the surface of the air gap, because that would be an area that the molten aluminum could flow out of. So you'd like to have your rotor have slots that are fully contained inside itself, so that your molten aluminum stays in there and the process just works smoother, and you can kick these things out at a higher quantity and rate. If you're going to use copper bars, you're going to want to have some kind of shape that you're able to insert the copper bar into. You're more willing to have an open tooth tip here. The tooth tip, this has strong implications for the leakage inductance of your rotor. We talked about where the leakage inductance, that's at R sigma value, appears in the equivalent circuit and the implications it can have on your torque speed characteristic. And so generally you'd prefer to have a lower leakage inductance of your machine because that presents lower impedance for your rotor. And so then with the copper bars, you're able to have that open tooth tip shape. Another consideration is whether this is going to be a line start versus a variable speed drive operated machine. And why this matters is it gets into what your torque versus slip profile looks like. And so let's develop that a little bit more. And so as we've been sketching it, your torque versus slip characteristic looks kind of like what I've drawn here, where you've got some maximum torque that's called your breakdown torque or your pullout torque, and it has a corresponding slip that it occurs at. And what you're nervous about when designing a line start induction motor is that your load torque somewhere in this region is larger than your electromagnetic torque, and you're never able to get up over here to a speed that resembles your desired speed, a speed that's closer to the synchronous speed. Ideally, you'd like to boost this torque up at low speeds to as high a value as possible to ensure that you get out close to your rated speed and desired operating condition. And it turns out that you can play some games with your rotor slot shape to help you accomplish this. If you solve that equivalent circuit that we sketched in a previous video, you can figure out that your slip at the pullout torque is equal to this expression under certain simplifying assumptions. And from this expression, we can see that we're able to change where this breakdown slip occurs based off of our rotor resistance. And so if we can somehow decrease our rotor resistance at low operating speeds, we can end up creating a torque slip curve that has a boosted torque value at low speeds. And it turns out we can do this by taking advantage of AC resistance effects. And that's the motivation for these kind of rotors that you're seeing here in the middle. So let's focus on this rotor shape here because it presents the most exaggerated situation. So in this rotor over here, at high values of slip, so say that your rotor is locked, you're going to see the maximum frequency of field going through your rotor, right? The frequency of the rotor field is just going to be equal to your stator's synchronous frequency or the frequency of your air gap field. And in that situation, your leakage inductance creates a high impedance. So these inner bars in here have high leakage inductance because there's a steel path for flux to flow. So these are going to inherently be very high leakage inductance conductors. And so at zero speed, this is going to have a high impedance because of the leakage inductance, and so we're not going to get much current to flow in this bar. All of our current is going to take this outer bar. The outer bar is smaller, so it has a higher resistance, and therefore we have a larger RR prime value. We have a larger rotor resistance as seen by the stator, and we get a boost in torque. Now, when we get to high speeds, we'd prefer to have a low rotor resistance for reasons related to efficiency, right? We want to minimize the I squared R losses in our rotor at rated speed. So at high speeds, or at speeds approaching the synchronous speed, our slip goes to very low values, and therefore the frequency that we see in our rotor fields becomes very low, and that leakage inductance does not create much impedance. And so our current is able to make use of both rotor bars and has a lower value of RR prime. So that's one way that you can try to carefully design your cage rotor to make these types of improvements for a line start motor. For variable speed motor drive, you have different considerations. You're less worried about the shape of your torque slip curve in this region because you're able to change the frequencies of your applied voltages to more advantageously operate your machine in its high torque per amp mode. Next, you're going to determine the required rotor slot area, just like we did in the stator winding design steps. And In the stator design steps, we use a current density, so we'll use a current density again for our rotor, as well as the rated rotor current, which we determined up here. We determined the rated rotor current over here based on the power factor of our machine and the rated stator current. So we know this information. Our KCU is our slot fill factor, and this depends on the type of winding that you are using in your rotor and the type of manufacturing technique. If you're using cast aluminum, your slot fill factor is essentially 1. It's very high slot fill. If you're going to use rotor bars and copper rotor bars that are inserted into there, presumably your slot fill factor is a little bit less than 1, just accounting for getting the rotor bar to fit and some clearances around it. That concludes the design sizing steps. So at this point in this process, you have a complete design sized out for your induction motor. And so to recap where we are at this video, we've completed this set of steps right here, and now we're going to outline FEA-based design evaluation steps for optimization. So the induction motor is a lot more complicated to analyze than our synchronous motors because of the rotor currents. Those rotor currents take time to build up and reach steady state. And furthermore, typically when we're trying to evaluate a candidate design, we don't know what the rated slip should be. We don't know where this pull-out slip occurs. We just generally don't know the frequencies that this torque profile appears at. So we don't know what speed to set our rotor at with our FEA tool. Generally, our objective with designing, with evaluating a design is that we're trying to calculate the efficiency of the design and the torque ripple of the design. But how can we calculate the efficiency of the design if we aren't operating it at rated power? So for this reason, we have to figure out what slip value our motor should be used at. And if we were just to use a brute force approach to modeling the machine, we would take a guess at our slip. We'd set up a transient solve and let it run. And then we would take another guess at our slip and set up another transient solve and let it run. And we'd repeat this many times until we extract out this torque slip profile. And then we would pick the slip point that corresponds to our desired rated condition and look at the performance that was evaluated for that design. However, doing that would probably take years. So typically, for an induction machine to reach steady state in even a 2D FEA solve, this can be something that takes on the order of several hours to several days. And this is far too long, right? If you're trying to perform a design optimization on an induction motor, you presumably have anywhere from 1,000 machines that you have to evaluate the performance of to 100,000 machines you have to evaluate the performance of. So we can't be sitting here trying to extract this curve here where every single point on the curve takes, a few hours to a few days to evaluate. So what I recommend based on research projects that we've done, is that we take a hybrid approach to evaluating design. And in this hybrid approach, in step 1, use an eddy current solver to estimate your torque versus slip characteristic. So if you remember back to when we introduced FEA techniques, we talked about 3 different types of solving strategies. The first was a static solver, and that's what most of our homeworks and theory has been developing so far. The second was a transient solver. A transient solver means that we've got conductivity turned on in our materials, and we use a time-stepping algorithm to solve our problem in time. So we have a certain time step size. We're solving time domain differential equations with the FEA tool, and it's the most accurate and most comprehensive solution technique. And then the third option was something called an eddy current solver or harmonic solver. An eddy current solver looks kind of like a static solver at first pass in that there's no time domain differential equation that's being solved. You're solving the problem one time, but you're solving it at a specified frequency. So the formulation for the differential equations that are being solved with the FEA tool is a steady state time harmonic formulation where you have omega appearing in the equations. And so if you specify your frequency of the machine excitation as being different estimates of your slip frequency, you're able to extract out this torque versus slip curve. So your rotor is held fixed at one position, you make a guess at what your slip frequency is going to be, you solve it and you figure out how much torque is on your rotor, and then you make another guess. So each of these points that I've sketched on here would correspond to a different solution. And this type of evaluation, if done in 2D, takes a few seconds, and so it's pretty quick. But it has limited accuracy because the fundamental premise of your eddy current solver was that you had to have linearized material properties. It's not able to deal with saturation in the steel. And so for this reason, you can't trust that this torque characteristic is actually what you're going to get out of your machine, but you can use it as a means of guessing where you should have your rated torque be at, right? So this gets you close. Then, in step 2, you take your results from your eddy current solves, you pick which slip you want to evaluate the efficiency and torque ripple of your machine at, and you do a transient FEA at that point. So remember, I said a single transient FEA solve might take several hours to several days. So what you can do to speed that up is you can take the results of your eddy current solver and use it to initialize your transient solver. You can load the rotor bar currents as having an initial value that was specified by the eddy current solver. And some transient FEA tools are actually able to load this BH curve state from an eddy current solve. And doing this helps the transient solver more rapidly reach steady state for the rotor currents and the overall solution space, because it gets you to a place on the BH curve where you're correctly operating at the correct level of saturation. And this is particularly important for induction motors because remember, induction motors typically have more saturation in them than other types of motors. They're typically operated with a little bit higher level of saturation. So at any rate, by doing this eddy current solver and initializing your transient solve with values that approximate the steady state values, you're able to expedite your transient FEA. And you can take other steps to try to expedite the transient FEA as well, such as using different time step sizes. So for example, you could use a very large time step size for one rotor revolution just to help the solver get to again steady state, and then switch to a very fine time step size for collecting all of your loss calculations. Okay, so with that said, that concludes this video. Let's summarize what we've done here. We have updated our analytic machine design sizing procedure for a cage rotor induction machine. And we've outlined FEA-based design evaluation steps that can be used with an optimization algorithm. So we've outlined steps that decrease our solve time to a level that we can actually link this up to an optimization algorithm. This whole video is intended to help you come up with an initial design for an induction machine that you would then refine based off of an FEA study or use as an initial template design for a population-based optimization. We use theory that we've developed in the course so far to come up with ways to determine key quantities in our machine design, whether it's our rotor current, our stator current, the size and dimensions of our stator and rotor slots. And finally, we've outlined an approach to linking, we've outlined a FEA-based design evaluation approach that can be used to model this machine for use with the optimization algorithm.